Hello everyone, my name is Luis Tristain and today we're going to talk about derivatives. By the end of this lesson, you will understand what a derivative is, how to compute it, and how it is used in the real world. You'll also see that calculus isn't just abstract math, it's a tool for understanding how the world changes. So before we start, let's do a quick warm-up. My question to you guys is, have you ever ridden a roller coaster and at what point do you feel you're going the fastest? Give it a second. Think about it. Because the steeper the track, the faster you're going. That steepness, that slope, is what we call the derivative. It's how we measure how fast something changes at a specific instant. Now imagine if we could zoom in on any part of the roller coaster and measure exactly how steep it is at that point. That's what a derivative does. It zooms in and tells you the slope right there. So now let's get more towards a textbook definition of what a derivative is. So the derivative of a function tells us how fast it's changing at any point. Graphically, it's the slope of the tangent line to the curve. Over here, I've graphed the function x squared. So my question to you guys is, from the graph you're looking at right now, is what happens to the secant line as the 2 points come closer? It becomes a tangent line. The slope of this tangent line is the instantaneous rate of change. That's the derivative. We can also define this slope mathematically with the limit definition of a derivative. Over here, I have the limit formula, which is the limit of h approaching 0 of f parentheses x plus h minus fx over h. I like to call this a zoom-in formula. We zoom in infinitely close to define the slope at just one point. Let's try it out with the function of x squared. We plug in x squared to the first part of the equation, which is f parentheses x plus h, which would then equal parentheses x plus h squared, and then it would equal x squared plus 2xh plus h squared. We then subtract fx, and by subtracting it, we take away the x squared, which will then give us only 2xh plus h squared over h. We then simplify by canceling out the h's, and then it would just give us 2x plus h. Since the limit here is h approaching 0, h equals 0. So the answer to this is 2x. Now, the limit definition is great for understanding the concept, but it can get very messy and tedious. So we use the derivative rules. Think of them as math superpowers, as kind of like a shortcut. The first rule is the power rule. What we do is that we drop the exponent down, subtract 1, and then boom. Very easy. So if they ask us to find again the derivative of x squared, we just drop the 2 down. That's it, 2x. Very easy. The second rule is a constant rule, which says that the constants don't change. So the derivative is always 0. So if they ask you, hey man, what is the derivative of 1 million? 0. What about 2 million? 0. A billion? 0. It's a constant. It will always be 0. Now the third rule is the sum and difference rule, which states that if they ask us to find the derivative of f plus g, we have to find the derivative of f and g. So let's do a quick example so you guys can see. Over here we have the function of 3x cubed minus 2x plus 7. The derivative of it is 9x squared minus 2. You see, we have to find the derivative of each of them. Over here, I have a list of functions to differentiate. So the first one is the function of 5x cubed plus 2x squared minus x plus 7. So the answer would be 15x squared plus 4x minus 1 plus 0. Why is 7 0? Because it's a constant. Then our second problem is a function of 4x to the fifth minus 3x squared plus 10. That would be 20x to the fourth minus 6x plus 0. Once again, 10 is a constant. Our third function is x to the seventh minus 5x cubed plus 12x. The answer is going to be 7x to the sixth minus 15x squared plus 12. And then our last function is 8x minus 9. And the answer is very easy. It's just going to be 8. Since 9 is a constant, it's going to be 0. So now since we're done with how to compute them, let's talk about a very interesting topic of derivatives, which is the real life applications of them. So the first one is physics. So how are derivatives used in physics? Very easy. Calculate velocity. What about economics? Calculate marginal costs. Biology, calculate their growth rate of a population, And video games, interesting, is to calculate the character speed in each frame. Very interestingly, this is just a small list. It can go on and on and on. I mean, they're everywhere. Derivatives are everywhere. They're the foundation for mathematics, which is why it's very important to know them. So thank you guys for listening to this quick crash course on derivatives. And as you can see here, we have one of the top 3 scientists, one of the top, I would say, not 3, I apologize, top 50 scientists here, which is, we have Einstein, we have Tesla, and we have Oppenheimer. And I can tell you for a fact that all of these scientists, they use derivatives in their work because they use integration. As you can see, and then integration, it progress to more complex mathematical topics. But as you can see, they all relate back to derivatives. So learn your derivatives, learn your derivatives, because trust me, you will always get back to them.